topic is benchmarking a high electron mobility transistor using active load pull between 120 and 170 gigahertz. The speaker is Professor Chung Lee from the University of Glasgow. Apparently Chung is on the move and I'm going to be presenting from the road. Welcome, Chung.
Hi, Steve. Hi, everyone.
I'll take 30 seconds and I'll introduce you, and then are you able to share your presentation from where you are?
Yes, I think so.
Okay, fantastic. Let me know if you can't, and I'll share it from my side. So Chung Lee obtained his PhD degree in electronics and electrical engineering from the University of Glasgow in 2012. From August 2011, he took up a post as a postdoctoral research assistant and later a postdoctoral research associate at the University of Glasgow, working on terahertz imaging systems. Chung joined the National Physics Laboratory in January 2014 as a higher research scientist, leading work on antenna OTA, ultra-fast and on-wafer measurements, and rejoined Glasgow University in August 2017 as a lecturer, and founded the Microwave and Terahertz Electronics Group. He is now a professor of microwave engineering and the director of the Center for Advanced Electronics. Chung, the floor is yours.
Thank you for the introduction. Unfortunately, I can't share my screen for some reason. I think there's something wrong with my laptop. I don't use that very often. So
let me do possible? It from my screen then.
Sorry about this.
No problem. It'll just take 1 minute till we're up and running. Give me a moment. All right, I'm unfortunately gonna have to share your PDF, but it should still be okay. So let's go from there. Does that look good?
Yep. Thank you. Okay. Hello, everyone. My name is Chung Lee. I'm actually presenting this work that was done and presented by my PhD student Jing Wang at the last ARFTAC in, I think, January. Yes, in January. So we would like to show you how we use this active load pull system from Mori and its partner Vertical, and that's called the active load pull system to characterize a commercial transistor that actually not designed for operating at a very high frequency. We want to just try to find the limits of this transistor, commercial transistors, so we can hopefully can benefit some of you who are trying to push the limit of your devices, right? So next, please. So here is the outline of my talk today. So I would like to give you a little bit of background about and motivation about the work. Although previous speakers have highlighted the need for high frequency transistors, but I would like to give you a little bit my perspectives, and then move to the device under test. So we, although the you can find some of the information on the commercial transistors on the website of the commercial transistors manufacturer, but we also characterize the devices by in our own lab and then using our own facilities. So hopefully can give you a little bit of foundation about my following discussion, and then move to the active load pull system that we're using to characterize the devices, and show you some of the results. And then we move to the conclusion and future work. To be honest with you, and I will not show you too much detail about the device under test because under NDA, but I can just briefly talk about what we do at the Glasgow University, probably slightly after showing the results. And actually, we also develop transistor technology at the Glasgow University. Okay, thank you. Next, please. Okay, one more. Okay, this graph shows, well, it's quite old. That was a few, almost 13, 14 years ago. This is an international technology roadmap for semiconductors. It shows the kind of the drive of the technology and applications on device development, okay? And I think that the more latest roadmap shows have some change on this graphs, but it show you anyway. And what I want to show you is, and from the communication, wireless communication point of view, the high capacity or high data rate links is unavoidable, right? It's moving towards to higher capacity, like we're talking about 100 gigabits per second, or even 1 terahertz, 1 terabit per second in the next generation of wireless communication. But this is based on the carrier frequency. We need a higher carrier frequency so that we can get a wider bandwidth, and therefore to get a high capacities, right? So how can we get there? We're talking about a few hundred gigabits per second data link. So we need to move 100 gigahertz or above in order to achieve that. Okay, next slide, please. So I borrow a slide from Nokia's Wild, so who presents this paper and this at the workshop at the European Microwave Conference in Milan, 2 years ago, 1.5 years ago. So the concept from Nokia for future communications is, it's trying to connect everything within the umbrella of 6G, talking about digital world, biology world, and everything to be connected by the network. And this adds a lot of burden on the front end, so transmitter and the receivers. So the transmitter and the receivers must do communications as well as sensing. Okay, so in order to achieve this complicated tasks, we have to realize using this advanced technologies, not only the digital part of that, but also the RF front end. So you can see on the right-hand side of the right bottom of the graph, you can see this complicated architecture system from the system level, and also even for the front end, right? So in order to achieve this communication and sensing and connect all this digital and the biological world. Okay, next, please. So transistors, previous speaker mentioned about gallium nitride HEMT transistor technology, but there are also other transistors, because the transistors are the core component in this all the RF system, right? They are very versatile. They can be used for not only the low noise amplifiers, power amplifiers, but it can also be used in other scenarios, like as switches, and it could be used for oscillators as well. There are other technologies apart from the gallium nitride, are including like indium phosphide, HBT, silicon germanium, and etc. So indium phosphide has been used for high frequency application for a number of years. I think so more than 2-3 decades. But there's still a lot of room to improve, right? Especially the new drives from the communication point of view, that for receiver, from the receiver, we need a high performance of transistors, indium phosphide transistors that can give you not only frequency but also low noise. Okay, so this table shows you some of the key parameters like gain and PAE. Of course, for low noise amplifiers, the PAE is not as critical as power amplifier, but still useful to know their efficiency, because I think this is not well, we have to be realistic that once we move to high frequencies, 100 gigahertz and above, and none of the available technology nowadays can give you relatively high PAE as what we can get at the low frequency range. We're talking about a few 10 gigahertz. Okay. Next, please. Well, I think most of you know already know this transistor technology, but what I want to highlight here is the T-gate process. That is the key for making the devices working at a higher frequency range. I think the state of art demonstrated well. We're talking about almost 9 years ago. There was a 25 nanometer indium phosphide that can give you some gains at a 1.5 terahertz, right? But still, lots of research going on in this field. Recent research found out that the gate, the length of gate, is not the only thing that can make you determine the FT and F max. Other parameters, for example, the parasitics and also the substrate, there's parasitic capacitance between source, drain gate, etc., and also the parasitic mode of propagation, like CPW mode and other microstrip modes, and the substrate could be a main factor determining the highest oscillation frequency and the cutoff frequencies. So there are so many things we can do to improve the performance of the transistors, apart from the device point of view. There's other parameters include like the materials, as we may know that the channel layer. So if you take a look at the left-hand side of the graph, that shows all the channel layer, all the epitaxial layers. You have a channel and space, barrier, etc. Optimizing the thickness and also the mole fraction of the materials, as well as the composition of the channels, can improve the performance, apart from the making a shorter T-gate. Okay. Other parameters, like the previous speaker mentioned, that the ohmic contact could be also something to work on. Okay, let's move on. So, okay, now let's move to the device to be investigated during our work, this work. So the device to be benchmarked is from Dynamics. The company developed this in the middle of the top middle of the page, show you the snapshot of the that's the SEM image of the device. You can see that there's the 4 fingers there, and there's air bridge connecting the fingers. But actually, the device under investigation is 2 finger, and the gate length is 100 nanometer. So pHEMT, as I mentioned at the beginning, so we're not allowed to show the epitaxial layers, but on the right-hand side, this dark green, sorry for the color, it's not quite clear. But I can say that the graph shows the noise figure versus frequency at the different temperatures. So, and the scale we're talking about from 0 to 1, the y-axis, right? So you can see that the device has really good performance, noise performance, right? So we're talking about under less than 0.5 dB under 30 gigahertz. So yes, of course, this device is the main selling point for this device is for low noise, but and then they only show the noise performance and up to 50 gigahertz. So when we got this device, we thought that we can do a little bit more than the low noise amplifier at up to 50 gigahertz. We would really want to see the real potential. Okay, so and also we would like to see how we can possibly improve the performance of the device from other aspect we showed early on. So on the bottom left, we show the IV curves, right? But on the right-hand side, we show this transconductance and the drain current. So we use the my student Jing use AI technology, try to optimize all the parameters, including the drain gate, sorry, the device, sorry, including gates. And we see that there's a potential to improve the devices by adding or changing some of the parameters, okay? But how far can we go from those parameters? I think we better understand the limit of the device, okay? So can we move to the next slide, please, Steve? Yes, so we use our existing system, test system in our lab to, basically S parameter, right? So the standard 50 ohm system, right, to measure the S parameter of the device. This is on wafer measurement. So we use two systems. One is from 10 megahertz up to 110 gigahertz. The other one covering up to 170 gigahertz. There's a small gap there between 110 and 120 gigahertz. That's because of with the probe we had couldn't cover this small range. That's why you see the gap on the left graph. Okay, so we also compare the measured results with the simulation. So we can see, if you can take a look, the purple curve, that's S21, okay? So this S parameters are measured under 50 ohm system. So this system can give us the maximum gain at 170, around 170 gigahertz. So it's about 1 dB or just almost, yeah. So that is the maximum frequency, right? So and then recently we acquired Morris system, and that allow us to do this active load pull. So we can see we want to test the device with the system and to see what about the at the other loading conditions. If we can extract the real performance of the device at different impedance. So can you move to the next slide? Okay, right. For the local system, I don't want to go to repeat more than because the previous speaker has already mentioned. But I want to ask, just add a little bit more. So for the low-power system, we can get a nonlinear behavior to find more information and try to drive the device and their limits in terms of power. We can get a large signal performance for the devices, but we also can do this, the non-50 ohm loading condition. That sometimes is very helpful for from device development point of view. Okay, so can we move to the next slide? So um, the passive load-pull system is limited by the tuner and also the system loss, right? So there's not much we can do, especially at a high frequency range, because the system loss is massive and critical. We talk about a few dBs. That also limits the cover the area of the Smith chart, right? So as you can see on the right hand side of the Smith chart, so the higher the loss, of course, the smaller area we can cover on the Smith chart. So that's not good for the device characterization point. Right? So next slide, please. The active system can really increase the Smith chart carrier area, and then we can get a better understanding of our device. Okay. Of course, that's also been limited by the power of the frequency extenders, as mentioned by Osman at the beginning. So move to the next slide, please. Yes, so the active low-flow system, Maury and his partners, Vertical, so it's shown here, right? And on the left-hand side, I show the diagram and the signal path. On the right-hand side, it shows the actual configuration in our lab. So we use MPI's terahertz probe station automated probe station. So what we show here is for 110 gigahertz configuration, but this can be extended to higher frequency range. We're talking about well, whatever the limit of the frequency extender you may have in your lab. Luckily, we have almost everything, or every frequency extenders up to 1.1 terahertz. So theoretically speaking, we can use the system to test the devices up to 1.1 terahertz in our lab. Okay. I think yes. So right. Yeah. This is the result I would like to show you. So the same device I showed you previously, as I mentioned, with a standard 50 ohm system, we can only get gain up to 170 gigahertz. But with this active low-power system, and that can give us wider load conditions, and then we can see the devices at different frequency. So especially at the maximum like a 170 gigahertz, we can see the graph on the left hand side. So so the bunch of sorry, do I have a cursor here? Can I? Not sure if you can use cursor. Okay, so the bunch of the curves on yes, on the left hand side. So, sorry, yes, that's right. Yeah, those bunch of lines show the gain. Okay, at 170 gigahertz. Sorry, at a different frequencies. Okay, so we're talking about the 120, 40, and 60, and up and 170 as well. Okay, and the bunch of curves on the bottom, yes, okay, those are the ones show the efficiency. Okay, PAE. So now we can see that even at 170 gigahertz, we can still get 4.5 dB gain, right? I know this doesn't seem to be a lot, but we can at least we can see that this we can potentially get higher gain with the different loading conditions. Okay, in terms of the efficiencies, we can get up to like a 12 percent at 140 gigahertz. So these are all we the manufacturer not what we initially aware of, right? So with this system, we can really see this potential, okay, of the device. Okay, so I think that probably I will stop here. Initially, I wanted to add a few more, a couple of more slides to show off, basically to show what we got at Glasgow University, because we also develop transistors, but because of the results have not been published. But I can say that we with our in-house transistors technology and the fabric, sorry, in-house clean room and the technology developed for transistors, our devices can work at more than 300 gigahertz, and some of the results have been submitted to IEE MTT, sorry, the device TED, and now under review. So hopefully I can show you in the near future. Okay, can we move to the next slide, please? So yes, right. I have shown you some the results. We used the active load pool system on commercial transistors, right? For and although these transistors have not been well developed for high frequency application, but mainly for low noise, you know, for probably for at a low temperature as well. But with this new development of technologies, we can really investigate the real potentials of the devices. Okay, and this also the system can also help us to characterize and find the limit of our own devices. Okay, so yes, I think probably one more. Yes, so for future development, yes, we don't just characterize devices, but also we need to use the measurement results to design or develop amplifiers, whether it's a low noise amplifier or power amplifiers. So and the modeling software and from the system will be used to model the device and develop low noise amplifier or power amplifiers. And we can do more with this system for at the different temperatures. So I haven't shown you the results, but we are investigating using the system for different temperatures that has not been widely investigated. And of course, this results or this system will benefit our transistor development. So, okay. I think that's probably everything. Finally, I will thank the founder of this system. So that's UK's EPSRC under this TIC60 grant. And I would like to thank my student and my other RAs in my group. Okay, thank you very much.